Okay, this is a recording of the lecture for Chapter 7, Lecture 1 in ME 1001 lab. And I'm probably not there because I am going to the Fluid Power Vehicle Challenge by the National Fluid Power Association because my husband, Rich Rahal, and I are co-advisors to the Kennesaw State Hydraulic Trike Team. So let's get started with our lecture. Just minimize this. Minimize this. So I should be sharing my screen. Okay, so this is lecture 13, and if it's not lecture 13 or we're not doing the same project in the subsequent semester, please ignore this part. But if you're doing the car launch, today the technical design reports and Chapter 6 homework are due. The car launch is in 2 weeks, or whatever competition we're doing, it's in 2 weeks. For the car launch, construction and testing, we're in that phase. You need to document your work. Don't forget to document your work with both pictures and videos, and take notes of any design changes as a result of fabrication and testing. You'll need to discuss those with the PowerPoint. Okay, so we're going to talk about Chapter 7, which is a very important chapter. We're getting into the topics of thermal and energy systems. All right, so what I'd like to do first is a video that describes or introduces this chapter. Okay, so letting go to the video. Actually, I know it's a little bit childish, but it's actually a really good video. Okay, so this is just shy of 5 minutes. It's about 4.5 minutes. I don't watch the very end when he just asks you to subscribe to his channel. Okay, so let's get started on this.
Professor Dave here. Let's learn about work and energy.
He knows a lot about the science stuff. Professor Dave explains.
Just like force, the words work and energy have a variety of connotations in common language. When we say work, sometimes we mean exercise. Other times we mean a place we go every day and do something to earn money. Energy is even more convoluted. We might say that today we have no energy, meaning we feel tired. Or we might use the term in a completely metaphorical way, saying that a person or a location has good energy. But once again, in physics, these words mean something very specific, and if we are to learn science, we must allow the rigorous definitions to replace the colloquial connotations. Work is defined as action done on an object whereby an applied force causes a displacement of that object. A basic example would involve pushing a box 10 meters across the floor. Work is equal to the magnitude of the applied force times the displacement of the object. So it has units of force times distance. If you push with a constant force of 100 newtons over the 10-meter distance, you would do 1,000 newton meters of work, which are equivalent to another SI unit called joules. This means that work can only be done when displacement occurs. If you push a brick wall with the same force for the same amount of time as the box, you may get very tired, but technically you have done zero work. In addition, only the components of the applied force that are parallel to the displacement are considered to be contributing to work. If you push the box with your arms parallel to the floor, all of your effort contributes to work done on the box. But if you are pushing at a downward angle, only the X component contributes to work, while the Y component does not. In such a scenario, instead of using W equals FD, we could calculate the work done on the box using W equals FD cosine theta, as this will give us the portion of the applied force that is operating in the horizontal direction. If theta is 0, meaning the applied force is horizontal, cosine theta will be equal to 1, leaving us with W equals FD. And if you were to push straight down on the box, theta will be 90 and cosine theta will be 0, meaning no work is done on the box and it will not move. any angle in between, and there will be some motion. We must bear in mind that work is a scalar, and it can be positive or negative. Work will have a positive value when the applied force is in the same direction as the object's motion, like when pushing the box, and work will have a negative value if the applied force is in the direction opposite the object's motion, like if your baby brother pushes the box the other way, but without enough force to stop it from moving forward. The sign on work is very important because it tells us if the speed of an object will increase or decrease as a result of applying the work. Energy, another elusive term, is quite simply the capacity to do work, and this is summarized in the work-energy theorem. This states that when work is done on an object, there will be a change in that object's kinetic energy, which is the energy of motion. This also means that an object in motion is able to do work on another object. The work-energy theorem brings together concepts from Newton's laws and kinematics to describe motion in a way that we will examine further in the next clip. For now, we must simply purge ourselves of any prior connotations of the word energy and understand that it merely describes a property of an object or system that can be transferred into another object or system, often in the form of work. There are different kinds of energy, including kinetic and potential energies, thermal energy, chemical energy, and more, and we will discuss all of these when the time comes. Once again, the SI unit for energy is the joule, which is defined as a Newton meter, even though energy is not always transferred in the form of work. But our understanding of energy will grow as we examine the various types of energy. So let's move on to that part of the course. Thanks for watching, guys. Subscribe to my channel for more tutorials. Support me on Patreon so I can keep making content. And as always, feel free to email me, Professor.
Okay, so I thought that was a really good video to introduce our subject today. And
DaveExplains@gmail.com.
stopped. Okay, so now let's go to the textbook lecture. So this field, this thermal and energy systems, encompasses internal combustion engines, aircraft propulsion, heating and cooling system, electrical power generation, lots of different things that are important to mechanical engineers. So in this chapter, it's going to introduce the physical principles and terminology needed to understand the operation and efficiency of such thermal and energy systems. All right, so we already saw this in the video, but mechanical energy, work, and power. So gravitational potential energy is associated with a change of elevation of an object that has a mass m within a gravitational field. So it's going to be the weight times the elevation, or so that'd be mass times gravity times the elevation, mgh. So you're going to be seeing this equation in physics. You'll get very, very used to this equation. If your height change if delta H is greater than 0, the potential energy increases as the object is being elevated. And so if just conversely, if the potential energy decreases, if the object is being lowered. The unit for energy and work, there are 4 units that are commonly used. You're going to see the, sure I didn't, know what? It skipped a slide. Oh, no, it didn't. Okay, I'm okay. Sorry. So the 4 units are commonly used for energy and work. You've got the foot-pound in the English system. You've got joule in the metric. You've got BTU, which we use in the English system, and then kilowatt hour as well. That would be metric. Converting between these systems, it's in table 7.1 on page 285. Okay, so that was the that was gravitational potential energy. Now we're going to talk about elastic potential energy. So this is the energy stored by an object when it's stretched or bent in accordance to Hooke's law. So it'd be like if you have a rubber band and you expand the rubber band, It's got some energy stored in it. The equation actually looks a lot like the kinetic energy equation, but you've got 1/2 times the springs elongation times springs elongation squared times the spring stiffness. Now you can use this equation even if your component doesn't actually look like a spring. Like you could have a beam and it would have some elastic potential energy. Doesn't look like a spring, but it still has elastic potential energy. And then we have kinetic energy. So kinetic energy is the energy associated with motion. It can be in the form of vibration, rotation, or translation, and that is 1/2 mv squared, where m is the object's mass and v is its velocity. Okay, now we're going to talk about work. So it's the product of the force over the distance that an object moves due to the effect of that force. So it is the force over a distance. So work is force times the distance. It's going to be in joules or foot-pounds. Now we have power. So power is defined as the rate at which work is performed. So the work per unit time. When a force performs work during the interval of time, the average power would be the work over the unit time. We typically use watt, which would be joule per second in SI, and then either foot-pound per second or horsepower in the customary system. I just want to note here that, okay, so power is work divided per unit time. So remembering that work, oops, I don't want green, I want white. Remembering that work is equal to force times distance. It's called the distance delta x. So this is equal to force times distance delta x per unit time. So if you look at this, something should leap out at you. This right here, the amount of distance per unit time. So the distance traveled per unit time is also known as the velocity, right? So you could also think of it as the force times the velocity. Okay, and we're going to have actually an example problem where we'll use that. Okay, so we have to ask the age-old question, how many DeLoreans would you need to produce 1.21 gigawatts of power? This is the question that man has contemplated since 1985, because as you might recall, that is directly from Back to the Future. So let's watch a clip of Back to the Future, an excuse to watch a good movie. Let's watch a clip of this, and I swear it does have a purpose. We're going to have an example problem based on this. Okay, so let's watch about 3 minutes of this excellent movie. Pay attention.
Hey, Doc, this is it.
Never mind that now. Never mind that.
Why, that's me. Look at me. I'm an old man.
I'm Dr. Emmett Brown. I'm standing here on the parking lot at...
Thank God I still got my hair. Well, what on earth is this thing I'm wearing?
Wow, this is our radiation suit.
Radiation suit. Of course. Because of all the fallout from the atomic wars. This is truly amazing. A portable television studio. No wonder your president has to be an actor. He's got to look good on television.
Whoa, this is it. This is the part coming up, Doc.
No. This sucker's electrical. But I need a nuclear reaction to generate the 1.21 gigawatts of electricity.
What did I just say?
Flux capacitor storage. This sucker's electrical. But I need a nuclear reaction to generate the 1.21 gigawatts of electricity.
1.21 gigawatts! 1.21 gigawatts! Great Scott!
What the hell is a gigawatt?
could I have been so careless? 1.21 gigawatts! Tom, how am I going to generate that kind of power? It can't be done, can it?
Doc, look, all we need is a little plutonium.
Oh, I'm sure that in 1985, plutonium is available in every corner drugstore, but in 1955, it's a little hard to come by. Marty, I'm sorry, but I'm afraid you're stuck here.
Whoa, Doc, stuck here. I can't be stuck here. I got a life in 1985. I got a girl.
Is she pretty?
Oh, she's beautiful. She's crazy about me. Look at this. Look what you wrote here, Doc. I mean, that says it all. Doc, you're my only hope.
Marty, I'm sorry, but the only power source capable of generating 1.21 gigawatts of electricity is a bolt of lightning.
What did you say?
A bolt of lightning. Unfortunately, you never know when or where it's ever going to strike.
We do now.
This is it. This is the answer. It says here that a bolt of lightning is going to strike the clock tower at precisely 10:04 p.m. next Saturday night. If we could somehow harness this lightning, channel it into the flux capacitor, it just might work. Next Saturday night, we're sending you back to the future.
It'd be great to continue, just watch more, but there's a point. Do you remember the question I posed? How many DeLoreans would it take to produce 1.21 gigawatts of power? So question, whoops, I went to the next slide, next one. So the question is kind of, why did Doc Brown freak out so much in 1955? It's a 1955 Doc Brown that freaked out. Why did he freak out so much when he heard 1.21 gigawatts of power? It's because a gigawatt is a lot of power. So this is problem 7.4. And in the movie Back to the Future, Doc Brown and the young Marty McFly need 1.21 gigawatts of power for their time machine. So first thing, convert the power requirement to horsepower. Okay, and then the second part. If a stock DeLorean sports car produces 145 horsepower, how many times more power does the time machine need? So how many DeLoreans would you need? Assuming you don't know when the lightning's going to strike, all you have is your DeLorean. How will it be enough? Like, how many DeLoreans would you need? Would you need 10 DeLoreans? Would you need 20 DeLoreans? Would you need 1,000 DeLoreans? Would you need like 100,000 DeLoreans? How many DeLoreans would you need to produce this amount of energy? So this is the question that we have. All right, so let's solve this. So we are given the power needed is 1.21 gigawatts. And what we need to do, find, of course, the first thing they're going to have to do is a conversion, as always, right? Lots of conversions. So the first thing we need to do is convert to horsepower. Luckily, this is what we kind of need to do anyway in order to solve this problem. See, the thing is that the DeLorean is given its power and horsepower, and we're asking, how many DeLoreans. So we need to convert the gigawatts to horsepower. And then B, how many, okay, so one DeLorean. Oh, I guess I need to put this up. One DeLorean, it's under the given, produces 145 horsepower. That's an accurate number. Okay, so how many DeLoreans to power the flux capacitor? All right, so my solution. All right, so the first part is just going to be a straight on conversion. Okay, so if I look at table, so I'm going to need the converting. the conversion, and it's in table 7.2. I find that 1 watt is how many horsepowers? Well, it's 1.341 times 10 to the minus 3 horsepower. So just a very, very small horsepower per watt. Okay, so let's do this straight on conversion. So the power is equal to 1.21 gigawatt. So how many watts is that? A giga. So a mega would be, well, obviously a kilo would be 1,000. A mega is 1,000,000. A giga, it's 1,000,000,000. So that is 1.21 times 10 to the 9 watts. And now let's go ahead and do the conversion. That 1 watt, I'll put that in the denominator, is 1.341 times 10 to the minus 3 horsepower. Okay, do the math, get out your calculator. We get the power needed is 1.623 times 10 to the 6. That is a large number. Totally right. A large number. So we have to have like 1.6 million horsepowers. So the second part is the number of cars. So we need 1.623 times 10 to the 6 horsepower. And the conversion unit here is that 1 DeLorean, 1 car, gives me what was 145 horsepower. How many cars? 11,200 cars. That is a crap ton of DeLoreans. So no wonder the 1955 Doc Brown had such a conniption when he heard that number, because he has a sports car more powerful than anything that was being produced in 1955, but he would have needed 11,200 of those suckers to be able to power his flux capacitor. All right, they have a problem. Okay, let's go on to the next problem. Not as much fun, but it's still kind of interesting. So if you recall, in the last lecture, we covered, or we should have covered, problem 631. So we had, so for the 2 cars in chapter 6, 631, how much power must the engines produce just to overcome the air drag at 60 miles an hour? So I have a screenshot here of what we did last time. So we have the different coefficients of drag of the 2 vehicles and the frontal areas of the 2 vehicles of a luxury sports car versus an SUV. And it asks for what the drag force was for each of them. So we found that the sports car had a drag force of 58.6 pounds, and the SUV had almost twice as much force of drag of 118 pounds. All right, so let's think again about what it's asking us. So I'm going to start the problem now. So we're given that luxury sports car and SUV on problem 631. The drag force of the sports car is 58.6 pounds, and the drag force of the SUV is 118 pounds. And also the velocity we're going here is 60 miles per hour. And in the previous problem, we went ahead and converted it to feet per second. And yeah, we're going to have to use that still. So that is equivalent to 88 feet per second. All right, so what we need to do is find how much power the cars must produce to overcome the drag force from air. So that'd be from air, the drag force, at 60 miles per hour. That's what it's looking for. Okay, so my solution. All right, so let's go back to that definition of power. So power, if you recall, was work per unit time. This is equation 7.5. What is work? Work is the force times the distance over which the force acts. That is equation 7.4. So let's play with these two equations. We have power is equal to work per unit time. So we could say that is force times distance traveled per unit time. And lo and behold, like I mentioned in the lecture, that should look familiar. That is by definition the velocity. So we need to take the force times the velocity. So not difficult. Oh, and in this case, the force we're talking about is which force? It is the drag force, because we're talking about the drag associated with the air coefficient of drag and so forth of these two vehicles. All right, so let's go ahead and find the power required for this for the sports car. That would be equal to the force of drag of the sports car times, I guess I don't need those, times the velocity divided, oh, actually not divided by anything, just those two. Okay, so that is my 58.6 pounds times my velocity. Okay, so we're going to use that 88 feet per second. So the power required from the sports car, if I multiply those two, I get 5157. And my unit is pound-foot per second. Does it say what it wants the unit in? Well, when we talk about this, about power in the customary system, US English customary system, we really talk about it in terms of horsepower. So let's go ahead and convert to horsepower. And let me see, that was table 7.2. I see that 1.818 times 10 to the minus 3 horsepower per foot-pound per second. Okay, so I'll do that. I'll put that in right here. So I'm going to multiply that by 1.818 times 10 to the minus 3 horsepower per foot-pound per second. Okay, so then those cross out. And the power in the sports car is 9.38 horsepower. We're halfway there. Now let's do the power of the SUV is equal to the drag force of the SUV times its velocity. So that was 118 pounds times the velocity of 88 feet per second. And now that I know that we need to do this conversion, let's just go ahead and do it right off. So 1.818 times 10 to the minus 3 horsepower per foot-pound per second. Again, foot-pound per second, foot-pound per second. So we're going to get this in terms of horsepower. So the power required of the SUV is 18.9 horsepower. So as expected, because the velocities are the same, the drag is like twice as much. So sure enough, it's going to require the drag force. So sure enough, it's going to require like twice as much power. So it's a little bit more than that. So the SUV, so let's think about what we've got here. The SUV needs greater than 2 times the horsepower of the luxury sports car. And this is just to maintain the 60 miles per hour, only considering air drag. Because we're only looking at the force associated with the drag of the air. So additionally, the vehicles, both vehicles are going to have to overcome additional drag. Let's call it rolling resistance. So there'd be additional rolling resistance. So where would we get that? Why would we have additional rolling resistance? Well, I'm sorry. Well, I think I misspoke. Additionally, sorry about that. Additionally, I need to overcome, sorry. Whoops. Okay. Additionally, we need to overcome the rolling resistance. And friction in the system. Lots of friction in the system. And you could have a possibly gravity if you're going up an incline. That would be something that also that you'd have to overcome. So I'll say possibly gravity if on an incline. So the SUV is going to need twice the horsepower of the sports car to maintain that, just from the drag. Now, the rolling resistance. Will the SUV have more rolling resistance, friction? And then if it's on an incline, the SUV will weigh heavy. It'll have more rolling resistance and friction. Probably. This is a luxury sports car let's say that they've gone to extraordinary lengths to try to reduce the rolling resistance and frictions. And frictions, from a whole bunch of different sources. And then also the sports car will be lighter weight than the SUV. So the whole possible gravity, if you're on an incline, that would be more substantial in the SUV as well, assuming it's heavier. Which the engine of the sports car, I guess, could be heavier, but they're probably going to use more exotic materials, more carbon fibers and Kevlars or whatever they need to do, aluminum to reduce the weight And so you need to look at what the weight would be as far as looking at the gravity that needs to be overcome if you're on an incline. All right. Moving on. All right. So now we're going to go on and talk about heat. What is heat? Heat is energy in transit. So this is a big definition. Heat is energy in transit. And the heat is in transit, the energy is in transit because it's going to, because of a temperature difference. So if you have a temperature difference between like two areas, the energy will transfer, and that, from because of the temperature difference, and that transit is heat. Heat will be transferred through three different techniques, three different ways: conduction, convection, and radiation. And then during design, MEs will exploit the properties of heat to manage temperature and to move that energy between locations. I mean, we want the energy going from one location to another in kind of a prescribed manner. So we exploit this, the properties of heat. Heating value. In a furnace, power plant, or engine, the energy output of the combustion process is measured by a quantity called the heating value. And that's H. It describes the ability of a fuel to release heat. A conventional unit would be megajoules per kilogram in SI and BTU per pound mass in the US customary. So what is pound mass? Not equal to slug, but it is a mass. It's the mass unit we use when we get into thermal and heat topics. So you need to know the US customary, and you also need to know it's called the US engineering system when you get into pound mass. You'll learn more about that later. More about the heating value. So in calculations involving the combustion of a fuel, the heat that's released by a burning mass can be given by M times H. So the heat is equal to the mass times the heating value. The heating values of fuels can vary widely based on their chemical composition and the manner in which they're burned. Okay, and then we have specific heat. Specific heat is the amount of heat necessary to change the temperature of a unit mass by 1 degree. Heat is not the same as temperature. Because remember, heat, where is it? Is energy in transit. It is not the same as temperature. But we kind of, in lay terms, when we're just talking, we often use those two terms kind of interchangeably, but they're not the same. Technically, they are different. Heat is energy in transit. Changes in temperature indicate that heat has been transferred. As heat flows into an object, its temperature rises from initial value to a final value, according to this equation. And then where M is mass and C is the specific heat. If the final temperature is greater than the initial temperature, Q is positive, the heat is positive, and heat flows into the object. But if the heat's going to be negative, if your final temperature is less than your starting temperature, and that means that heat is flowing out of an object. So positive heat means that the heat is flowing in, and you'll have an increase in temperature. Negative heat means the heat is flowing out, and you'll have a decrease in temperature. The units for specific heat would be kilojoules per kilogram degrees Celsius and BTU per pound mass degrees Fahrenheit in the two systems. The physical property that quantifies the amount of heat that must flow in or out of material to produce a phase change is called the latent heat. I just want to take a quick peek at something to make sure that I didn't, oops, that's not right. That's the wrong one. That is bylaws. So let's see, here it is. Yeah, so we're going to do this next problem, and then we're going to have our next video about conduction, convection, and radiation. Okay, so this next problem, get my notes up to the same thing. Okay, so the heating value of agricultural residue biomass. So agricultural residue biomass would be like crop residues, animal manure, bedding, organic material from food production. There's going to be lots of things, lots of residue biomass that comes from agriculture. And the heating value can range from 4,300 to 7,300 BTU per pound mass. How much heat is released when 500 kilograms of biomass is burned? Okay, so let's set this one up. So we are given, we have 500 kilograms of, let's just call it biomass. And the heating unit would go from 4,300 BTU per pound mass to, this is going to be our H, to 7,300 BTU per pound mass. Okay, so where H is the heating value. So what I need to do is find the range of heat. And heat would be my Q. Okay, so solution. All right, so let's look at the definition of heat. So equation 7.6 tells me that heat is equal to mass times the heating value. This is equation 7.6. Okay, so we're gonna have a problem here with our units, right? Because it's giving my mass in terms of kilograms, but the problem is going to be in terms of BTUs, mass in English. So let's convert kilograms to pound mass. This pound mass is the mass unit I will use when I'm talking about heat. All right, so we're going to need to look at table 3.6. So from chapter 3, there are 2.2046 pound mass per kilogram. All right, so no problem. I'm actually just going to do it within the equation. So let's talk about our low and high values of Q. Those would be related to the low and high values of the heating value, excuse me. So my low heat would be mass times the low heating value. So it would be my 500 kilograms times the conversion of 2.2046 pound mass per kilogram. And then times the heating value of the lower heating value was 4,300 BTU per pound mass. Okay, so kilogram, pound mass. Sure enough, I'm getting my heat in terms of BTUs, which is just perfect. So the low amount of heat would be 4.74 times 10 to the 6 BTUs. And then I'll repeat that for the higher value of the higher heating value. I'll call that Q high. It's going to be the same mass times the heating of the high heating value. So again, 500 kilograms times 2.2046 pound mass per kilogram times, that was 7,300 BTU per pound mass. And again, I will get it in terms of BTU. So the high value turns out to be 4 points. No, that's not 4.74. That was the previous one. 8.05. Again, times 10 to the 6 BTU. It's my high value. So I'll say the heat will range between 4.74 times 10 to the 6, so 4.74 million BTU to 8.05 times 10 to the 6 BTU. Is that a lot of heat? So if we burn the biomass, is a lot of heat? Well, it's a substantial amount of heat. But not as much as you'd get if you burned wood or fuel or coal. So is there any point to do it? Well, yeah. What is the point here? It is still, it might not be as much as if you were burning wood or coal, but it's still a lot of heat, substantial amount of heat. And so what's good about this? It's potential heat from an alternative energy source. And you could say even in some ways a renewable energy source. Cow manure, you could think of that as like renewable because it's going to come every single day. Okay, so now we are going to watch a video about conduction, convection, and radiation. Just when you're getting super, super, super sick of me talking, I will stop. Okay, this is a pretty good video. This is about 3 minutes.
Thermal energy moves in three main ways: conduction, convection, and radiation. The movement of heat within a solid object is called conduction. Conduction also occurs when objects are touching. Look at the kettle on the stove. Heat from the flame moves through the metal of the kettle to the water in contact with it inside. This is an example of heat conduction. Butter melting on a fry pan is another example of heat conduction. When you lick an ice cream, it feels cold because heat conducts from your tongue to the ice cream. The movement of heat in liquids and gases is called convection. The air in a hot air balloon is heated by the burner and rises up inside the balloon. As the hot air rises, the cooler air falls and creates a current within the balloon. The convection current causes thermal energy in the air to spread through the balloon. On a hot day, you might cool down a room with an air conditioner. The cold air that blows out from the air conditioner circulates around the room and creates convection currents. Heat moves from the warmer air to the colder air, which makes the air in the room cooler. Cool, hey? For the thermal energy to move by conduction and convection, it must travel through matter. Between the sun and the earth is empty space. How does the heat from the sun warm the earth and other planets in the solar system? The answer is radiation. Radiation is the transfer of energy through electromagnetic waves. Look at the man warming by the fireplace. The heat from the fire warms the air in the room through convection. However, the man also receives warmth from the fire directly through radiation. The warmth you feel when you place your hands near an electric heater or a campfire are examples of heat in the form of radiation. We can observe conduction, convection, and radiation when water in a kettle is heated. Thermal energy moves through the metal to the water by conduction. Thermal energy moves around the water through convection. And finally, the heat leaves the kettle and is transferred to its surroundings by radiation. I hope you had fun learning about heat. See you next time.
Fun, fun. Fun now. Okay. So, I thought that was a pretty good video. I thought the examples were really kind of relevant and clear. And now I'll muddy it all up by going through a lecture. Okay, so transfer of heat, conduction. When you grip the hot handle of a pan on a stove, you feel the conduction in action. Heat is flowing from the pan along the length of the handle to its cooler free end. The quantity of heat that flows along the rod during the time interval of delta T is given by Fourier's law of heat conduction. The material property kappa is called the thermal conductivity. When the thermal conductivity is large, heat flows through the material quickly. Inversely, if it's small, it would be not flowing so quickly. Metals generally have large values of thermal conductivity, and insulators such as fiberglass would have low values. Convection. Heat transferred by a fluid in motion is known as convection. The cooling system of an automobile engine, for example, relies on convection. There's two types of convection. You've got natural convection. That's when you have fluid motion due to buoyancy forces created by temperature variation. And you've got forced convection. That's when fluid motion is due to external sources such as fans and pumps. Okay. And then thirdly, we have the radiation. Radiation is the heat transmitted by long infrared waves of the electromagnetic spectrum. These waves can propagate through air and through the vacuum of space even. Energy from the sun reaches the earth through radiation. I think we all know, but that's what this means. As the electromagnetic waves are absorbed by air, land, and water, they are converted to heat through radiation. Right, so we're just have one problem left, and then we will be done. Okay, so we have a 2,500-pound car that comes to a complete stop from 65 miles an hour. 65 miles an hour to stop. If 60% of the braking capacity is provided by the front disc brake rotors, determine their temperature rise. So we know that they're made of cast iron. There's going to be two cast iron rotors, and they weigh 15 pounds, and they have a specific heat of 0.14 BTU per pound mass degree Fahrenheit. All right, so lots of given information here. So given, we've got the mass of a car is equal to 25 No, that's not the mass. Sorry, that's the weight of the car. Got this big old one. Hold on. Mess this up here. Oh. Okay. The weight of the car is equal to 2,500 pounds. And the velocity goes from 65 miles per hour to 0. And we know 60% of braking is from front rotors. And we know that we have 2 cast iron rotors, each weigh 15 pounds. This is the total weight. 30 pounds. How did I get that? Okay. And lastly, the specific heat. So the specific heat of this cast iron is going to be 0.14, kind of crazy units. The unit is BTU per pound mass degree Fahrenheit. What I need to do is find temperature rise in the rotors. How hot will my rotors get? All right, so we're going to have to think this through. Initially, the car's going at 65 miles an hour. That kinetic energy will be converted to heat and then stored as the temperature rise. Okay, so let's go over that again. The kinetic energy of the car is converted to heat of the rotors, brakes, and stored as a temperature rise. Okay, so we've got some equations here. So first of all, I've got my equation for kinetic energy. That's 1/2 mv squared. Mass of the car, because we're going to have 2 masses going on, the mass of the car and the mass of the rotors. And then v squared. And then the heat, we were told 60% of braking capacities from the front disc rotors. The heat is going to be 60% of this kinetic energy. So the 60% of the kinetic energy is going to be heat in the rotors. The front rotors is what we're talking about here. All right, so now let's go to our equation. So our equation is that heat is equal to mass, this would be mass of the rotors. We're talking about heat of the rotors. Is going to be equal to mass times the specific heat of the rotors times this temperature difference. And this is going to be equation 7.7 in the textbook. Okay, where C is specific heat. And then T minus T naught, that's going to be my temperature rise. That's actually what we're solving for. right? Because it wants to know the temperature rise in the rotors would be the mass of the rotors times the specific heat times the temperature rise. That is going to be equal to the heat. All right. Well, let's figure out first the mass of the car. That'll be an easy conversion. The car, well, that'd be the weight of the car. Oops. Smaller. Should be a sub. Divided by gravity, right? So that would be my, what's it, 2,500 pounds divided by 32.2 feet per second squared. What unit will this give me? About that. What unit will this give me? This is going to be 77.64. So a pound is equal to a slug foot per second squared. So I'm going to have a slug here. So my unit for mass of the car will be slug. Mass of the rotors. When you get into this, you will find out that when you're using these thermal units of pound and pound mass, that they're actually going to be equivalent in value. So the mass of the rotors is just going to be 2 times the 15-pound mass. So I didn't really say that. Okay. So they each weigh 15 pounds, which is going to be equivalent to 15-pound mass. I know that seems crazy because they should be off by 32.2, right? Slug is different than pound mass by a factor of 32.2, gravity. It's not so simple when we get into the thermal and heat, because the unit would be pound force, LBF. The value is going to be the same as a pound mass. You will deal with this later, so just take my word for it right now. So this is going to be equal to my 30-pound mass. Okay. Well, you know that velocity is going to be a problem in miles per hour. Let's go ahead and convert that to feet per second. So my velocity is 65 miles per hour times, see, it's 5280, right? 1 mile, that many feet, and 1 hour is 3,600 seconds. So this turns out to be 95.33 feet per second. All right, now what? Kinetic energy of the car is converted to heat. So let's go ahead and calculate the kinetic energy of the car. So it's going to be 1/2 mass of the car times velocity squared. So we can do that. The kinetic energy, 1/2 mass of the car times velocity squared. It's 1/2. That was 77.64 slugs times my velocity is 95.33 feet per second, and that is squared. Okay, so the value I'm going to get here is 3.528 times 10 to the 5. We're going to have some messed up units. Slug foot square per second squared. All right, so what are we going to do about that? Well, remember weights is equal to mass times gravity. Just looking at the units, I would have pound is equal to slug times foot per second squared. So, what am I going to have? I'm going to have this many. Oops, I'll change back to blue. I'm going to have this many. Okay, if I can get rid of slug foot per second squared and instead put pound, slug foot, so I'm going to get just rid of the exponent there, second squared. This is going to give me a pound. And I still have a foot left over. So that's a pound foot, or as we more conventionally call it, a foot pound. Okay, super. So this is the kinetic energy of the car. Now, that's going to be converted to heat. And 60% is going to be from the front rotors. So the heat, oops, I don't want that, is going to be right there. 60% of my potential energy, it's going to be kinetic energy. So the heat so what will my unit be? Well, my unit for heat here will be the same as the unit for kinetic energy. But that's not quite right. When I'm talking about heat, I'm going to want to try to get it into BTUs. So I'm going to go ahead and convert here to BTUs. And that conversion is 1.285 times 10 to the minus 3 BTU per foot pound. Because when I'm talking about heat, I'm going to want to get the unit in terms of BTU, not foot pound. So my heat is, this turns out to be pretty even, 272 BTUs. Alrighty. I've got the heat. Now I can go into a temperature change because there's a relationship between temperature change and heat. It's that equation right here, my 7.7. So I'm going to take the mass of the rotors times the specific heat of the rotors times the temperature change is equal to heat. Okay, so let's go ahead and look at that equation. So the heat is equal to the mass of the rotors, so that's what's heating up, times the specific heat times this temperature change of T minus T naught. Well, the temperature change is what I need to find. So let's rearrange this so that my temperature change will be Q, the heat, divided by the mass of the rotors times their specific heat. Because it's the mass of the rotors, that's what's heating up, not the car, so I'm not going to use the mass of the car. So that is going to be 272 BTU. Mass of the rotors, 30-pound mass, 30 lbms. And then the specific heat was 0.14. Remember how we said it? I said it has crazy units. The unit of specific heat is BTU per pound mass degree Fahrenheit. This is good for us, right? So BTU is going to cross out, pound mass crosses out, and degrees Fahrenheit is in the denominator of the denominator, so we'll pop it up to the numerator. So T minus T naught, let's get the number, 64.76 degrees Fahrenheit. So I should say that's 64.8. And that's my answer, and I'm sticking to it. Okay, so just in the time that it takes you to stop from 65 miles an hour, just in that time, it will produce 60, almost 65-degree increase on the brake rotor, the front brake rotors. So this is a pretty big increase in temperature in a short time. So you wonder why the brake rotors might be made of cast iron. It seems like kind of in some ways, like an old-fashioned material. It's because iron absorbs and dissipates heat well. That's why it would be used to cool the brakes. So they're very specific on their selection of material for this. All right. So I went from 65 miles an hour to 0. Think about this though. If my velocity increased, what'll happen to my kinetic energy? It's really going to increase, right? Because kinetic energy is 1/2 mass velocity squared. So it's related to the velocity squared. So if I increase the velocity from 65 miles an hour to 85 miles an hour, that increase in velocity would have a huge increase in the kinetic energy. And so the kinetic energy is going to be is going to give me the heat, which is directly proportional to the temperature change. So the temperature change, whoops, go back to black here, T minus T naught, that will also increase a whole bunch because we only have a 20, if we went from 65 miles an hour to 85 miles an hour, it's only a 20 mile per hour increase, but that's squared for both the kinetic energy and the heat and the subsequent temperature rise. So this has just been a little bit of fun with chapter 7. This is chapter 7, lecture 1. We've covered, I think, some pretty good things today. We talked about power and energy, potential energy, kinetic energy, work. Power is work per unit time. And we also talked about, talked quite a bit about Back to the Future, so kind of like that. And then we talked about heat and what heat is. Heat is not the same thing as temperature, but they go hand in hand. But it's the transfer of energy. That is what heat is, energy in transit. And then we talked about conduction, convection, and radiation. Okay, so homework. What should you do? You should read chapter 7, and then if you're doing a car launch, assuming it's, the semester where I'm recording this or whatever competition I might be doing in subsequent semesters, build and test And then the competition will be in 2 weeks. This is week 13, and I always have a competition in week 15. So don't forget. But also read chapter 7. Okay, so that's all she wrote. I'm going to stop. That's a lot of Laura, especially it is 12:35 a.m. That's a lot of Laura late at night. A lot of Laura anytime. Let me stop the recording. Thank you for watching. Thank you for your attention. And I will stop the recording. Bye, everybody. And of course, contact me if you have any questions. That goes without saying. Bye.